metal. So we want nano zero valent iron. So we have ball milled it to take it nano zero valent iron, and then we have prepared contaminated solutions of fluorine, chromium and arsenic, and we have treated to get efficiency of NZVI. There are some sources of polyphenol which are green tea extract, tannic acid, Kerala, neem, cloves. Cloves is major source of polyphenol, but green tea leaves gives better efficiency, so we have used green tea leaves. Now, how we have used how we have made NZVI? We have taken green tea extract. Green tea extract is basically made by boiling the green tea leaves and then filtering it in the filter paper. Now we have used different iron compounds like ferric chloride, ferrous sulfate, Fe3O4 also we have used from HSM scale, and it turns to intense black color purity. The characterization of NZVI is that it shows intense black color purity. Now the solution is acidic in nature, so we have taken it to basic medium to get neutral solution, neutral powder, and this is NZVI. This is ZVI, sorry. This is ZVI, and we have to ball mill it to get nanoparticles. This is the same image which shows that there is a nanovalent iron. Now results. We have used different concentration of green tea for different iron compounds. Like we have used for ferric chloride, we have maximum efficiency we got it 90.92 with the 1% green tea. And we have again used Kerala extract over the green tea extract with ferric chloride solution, but we get very less efficiency. We can see 14.7 and 25.62. So it's better to use green tea extract with the ferric chloride solution. Now, as our innovative idea, HSM, we have treated it with the green tea. We got definitely less efficiency. But it is useful for us because FeCl3 is something costlier than slag. So we are using slag to get an NZVI which is better. Efficiency is, I think, low, but it's useful for us. Now testing results. We have prepared a dichromate solution, which you can see it was earlier yellow solution. And by treating NZVI with it and then filtering it, we got the colorless solution which clearly shows that NZVI is a good reducing agent, and it is clear water we can see. It means NZVI is reduced, the contaminants present in the water. Now comes to conclusion, as we can see by that NZVI is a better reducing agent as well as absorption, as well as it can reduce as well as it can do adsorption too. Now, if we go on filters, means if we make filters and use NZVI as a adsorbent, then it would be more cheaper and inexpensive and efficient for us. It can be, and we have reduced the size. It means we get it to nanoscale state, which increase the surface area, which increases the adsorption, means which results in the increase of the efficiency. So in the next step, we are trying to do design the filters. Means we want to make filters using NZVI, which we are carrying on later. Thank you so much.
One question.
Any questions, please?
Chromium 6 concentration. How did you compare? What is the initial chromium 6 concentration and the final chromium?
We have given it to NML. Means we have judged only by color. It was earlier pale yellow solution, and it is now colorless. We have given solution to NML. They will tell about it. The results are yet to be available.
Because it should be below certain ppm level.
Yeah. Its limit is 0.05 milligram per liter. So it should be. Means we have made 100 times of that. Means we have taken 5. That solution contains 5 milligram per liter solution. Means we have made 100 times of the limit set by the WHO. So definitely it would be. It would NZVI would reduce at least 10 times. So it would be below 0.0. Anything? Okay.
Good morning, everyone. Myself Prabhatma from IIT Kharagpur.
Myself Shubham Keshavani, I am also from IIT Kharagpur.
And our project mentor is Mr. Manish Kumar Bhagur. Our project topic is permanent magnets from steel industry bioproducts. So we are trying to form hard ferrite by using waste slag and red oxide, that is alpha Fe2O3. As we are concerned with the magnet, there are three magnetic properties: MS, MR and HC. MS is saturation magnetization, that is magnetization at saturation level. MR is remanent magnetization, that is magnetization when magnetic field is zero. And HC is coercivity, which means that it is the measure of the inverse magnetic field required to get magnetization to zero once they achieve saturation level. So hard ferrites are the ones which have larger coercivity. As you can see, these three hysteresis loops. The middle one is for soft ferrite. It has smaller coercivity, and the loops on the either sides are for hard ferrites, and they have higher coercivity. We can get higher square hysteresis loop if the materials have large coercivity as well as smaller value of MR and MS, and their MR-MS proportion approaches to 1. So we kind of try to get hard ferrites for having square hysteresis loop. Ferrites have nowadays become very important materials commercially and technically, as they have a multitude of applications. Basically, they are compounds with distinct magnetic properties such as high coercive value and high magnetization value. They are mainly used in electronic devices involving microwaves, magnetic recording and data storage media like hard disks, RAM, and as well as permanent magnets. Coming to their properties, ferrites are all very magnetic materials, and their magnetic properties are linked to their crystalline structure. For example, hexaferrites have hexagonal structure, and metal cations are distributed at octahedral and tetrahedral sites. They have a unique property called magnetocrystalline anisotropy, which tells that induced magnetization has a preferred direction. That is, within their crystal structure, they have high magnetization value in some specific directions. This is our literature survey part. So from our background study from various journals, we have found out that the doping of most of the metal cations in ferrites increase their coercivity. As you can see in this table 1, which shows the effect of doping of aluminium ion in strontium ferrite SR8012-490. As we are increasing the concentration of aluminium ion, MS and MR value is decreasing and HC value is increasing. MS and MR value mainly decreases due to the decrease in exchange interaction between AP3+ at octahedral and tetrahedral sites. And basically, aluminium cations have a strong preference towards octahedral sites. So they decrease the number of uncompensated spin electron, and that's why magnetization decreases. And HC increases mainly due to increase in magnetocrystalline anisotropy and decrease in grain size or lattice content, which we can get from XRD report. And in similar way, this is figure 1, which shows the doping effect of silica and cobalt ferrites. It is showing that as we are increasing the weight percent of silica, MS value is decreasing and HC value is increasing up to a certain doping limit. So we have found out that the doping of various metal cations like aluminium, calcium increases the coercivity of ferrites. So, but our innovation part is we are not using direct metal cation substrates like aluminium nitrate or calcium nitrate. We are using slag, which already contains these metal oxides like calcium oxide, silica, alumina in a much larger proportion. So we are using this slag and iron oxide to produce ferrites and to create some value addition to the industry. So now, Subhamu, question.
I am going to tell about the experimental part which we have done. So as we can see, this is the experiment flow chart. Basically, we are trying to make two types of ferrite, that is the barium ferrite and the strontium ferrite. Initially, we have taken the slag, iron oxide, and the barium carbonate and the strontium carbonate. We have stoichiometrically found that the barium carbonate or the strontium carbonate is required in 11 gram for the 100 gram mixture of slag and iron oxide. So we have weighed the proper amount. After that, we have homogeneously mix these materials in the pulverizer. After that, we have given the samples for the heat treatment. As we can see in the picture, the samples have been taken in the furnace. In the heat treatment, the samples are calcined at 1100 degrees Celsius for 1 hour, and the rate was 5 degrees Celsius per minute. And the cooling is done through the furnace cooling. Basically, the heat treatment is done to increase the crystallinity and also to remove the organic materials which are present. After doing the heat treatment, we have given the samples for grinding, which converts the samples. After the heat treatment, the samples got something accumulated. So basically, we grinded the samples and make them in the powder form, which are then we given the samples to the XRD and VSM results. We have got our XRD and VSM results, and then we done our analysis and found the samples. First of all, this is the strontium ferrite samples. The samples are named from PK1 to PK7. As we can see, the slag is decreased from 100 gram to 0 gram, and iron oxide is increased from 0 to 100 gram. Basically, we are trying to make constant the strontium carbon at 11 gram and trying to make constant the slag plus iron oxide to be 100 gram. And this is the preparation of barium ferrite. In the barium ferrite, we have taken barium carbon instead of strontium carbon as in the strontium ferrite. The samples are named from SK1 to SK7. The slag content has been decreased from 100 gram to 0 gram, and similarly the iron oxide content is increased. These are the results which we have got. These are the VSM results. As we can see, from PK1 to PK7, we have increased our slag content from 100 gram to 10 gram. And in the PK6 samples, we have got the maximum axis, which is the porosity. And our sole aim was to increase the porosity for the permanent magnets. We have got the 4000 porosity, which is also greater than the PK7 sample, which contains only iron oxide. So basically, we are trying to dope with the silica. We are trying to dope with the slag, which contains the aluminum and silica, to increase the porosity. And we have found in our result that the porosity is much more when we use only iron oxide, that is the PK7 sample. And the last column showing the VHMS, which is the energy project. It is basically the energy which is stored inside the magnet, and we can find that the energy content is also very good. We have also checked many companies which make the permanent magnets, and we have found that our energy product is somewhat in range, and we have made most of their products. These are the two graphs which are showing the hysteresis group. The lower one is for the low porosity, that is for the PK1 samples, which is around 60, and the above one is the higher porosity, which is about 4000. So conclusion, we have got our good results when the iron oxide content is 90% and the slag is 10%. So we can use this percentage to increase the porosity and make permanent magnets. Next, we can do the compaction of these magnetic materials to obtain actual magnets, which can be used in many devices as possible.
No question. Thank you.
Mentors and dear friends, my name is Maniranjan. I am a BTech student from NIT Durgapur, and my mentor is Mr. Kritik Sahu, who is principal researcher at Tata Steel R&D. I have done a project work on the use of graphene oxide as an alternative to liquid carbon sources in the mold powder for better melting control. First of all, let us understand the role of mold powder in continuous casting process. Here is a schematic of the continuous casting process where the mold powder is shown. At first, the mold powder is added on top of the mold to cover the liquid slag, liquid steel. This liquid steel is at a temperature of around 1600 degrees Celsius, which heats up the powder layer. At such a high temperature, the carbon in the powder layer starts budding off, and as a result, the sintering starts. This sintering at higher temperature, the sintered layer melts to form a liquid slag pool. This liquid slag pool will fall into the gap between the mold and the liquid steel to provide lubrication to the solidified liquid steel itself. Now, let us understand the role of carbon in the mold powder. This carbon has a bad bending property, uh, towards the slag particles, which will this carbon will form a network or skeleton between the slag particles, which will prevent the formation of agglomeration of the slag particles. And as we can easily see that if the carbon particles are small in size, then the melting rate or the agglomeration will be more, and therefore melting rate will be higher. Now, different carbon sources that are used in our mold powder are graphite fines, coke fines, and carbon black. Their particle size are of the order of micrometers. But now we are using graphene oxide. It has a particle size of around nanometer. It is around 1 or 2 atoms thick. It is around nanometer size particle. So its melting rate should increase, and it should have a better slag pull length. Now the experiments that we have done, we have taken 3 mold powders for our study, and we have removed their carbon content by decarbonizing them at 700 degrees Celsius and held it there for 3 hours so that carbon completely burns off. We have added graphene oxide according to the following table. We have the powder A. We have taken 3 powders, powder A, powder B, and powder C. This powder A contained 14.7% carbon. We removed it and we added 15% graphene oxide and 10% graphene oxide. In powder B, there was 6.6% carbon. We added 6% graphene oxide. In powder C, there was 5.66% carbon, and we added 6% graphene oxide. Now, the 3 powders had an increasing trend of basicity. Powder A had a basicity of 0.64, powder B a basicity of 0.86, and powder C a basicity of 1.15. We have done 3 tests: heating microscope test, DTA-TG test, and fluidity test. In powder A, there was a rough increase in the melting behavior. Sintering temperature increased, deformation temperature increased, hemisphere temperature increased, flow temperature was almost similar. Flow temperature was almost similar. This can be explained as a carbon wholly burnt out. Then the mold powder composition was same. So at flow temperature, they behave similarly. On effect on the melting rate, we measured the fluid length, and there was a decrease in the fluid length when we increased the graphene oxide concentration. This is the TG result for powder A. For powder A, this green color line is for the actual powder that contains carbon. That showed a huge mass reduction at around 700 degrees Celsius. But for powder A containing 15% graphene oxide and 10% graphene oxide, this indicated by these red and blue lines, there was no burning of graphene oxide till 1200 degrees Celsius. However, there was a mass reduction at 1200 degrees Celsius in all the 3 samples. For powder B and powder C, there was a different result. For powder A, we had seen an increase in the trend, but in powder B and powder C, there was a decrease in the trend. Sintering temperature decreased, deformation temperature was increasing, hemisphere temperature was also decreased by 1 degree Celsius here, and flow temperature was almost similar. In powder C, this melting trend has also decreased. Sintering temperature has decreased, deformation temperature, sphere temperature, hemisphere temperature, and flow temperature all has decreased. Now, seeing the fluidity behavior, for powder B, the fluid length increased, but in powder A, the fluid length has decreased. And with powder C also, the fluid length has increased. The TG results for powder B and powder C shows that there was this red line in both the graphs is for actual powder, and for this green one is for the graphene oxide. For powder B and powder C, there can be seen a huge mass loss in both the powders. This indicates that there was a burning of carbon, but there is no mass loss at 700 degrees Celsius for powder B. There is some weight loss for powder C at around 800 degrees Celsius. This indicates that for powder C there was a burning of graphene oxide, but for powder B there was no burning of graphene oxide. This can be further experimented, know the results for the basicity, the dependence on the graphene oxide behavior. Now the observations, we have seen an decrease in the fluidity behavior for powder A. For powder B and C, there was an increase in fluidity. We have also seen that graphene oxide is potentially affecting the thermophysical properties of mold powder. There was a sudden weight loss in powder A, when there was normal carbon at around 650 degrees Celsius, but for powder A containing 10 and 15% graphene oxide, there was continuous weight loss till 1200 degrees Celsius. Now, this is a huge discovery, so there might be a lot of future work on this. Some of these are, we can understand the relation of basicity on the fluidity behavior in the presence of graphene oxide. We can also study the microstructural property relationship at higher temperature of the powder, and also we can do the imaging analysis to see if there is any extra phase present due to the presence of graphene oxide. At last, thank you.
Why did you take graphene oxide?
Well, sir, as I said earlier, it has a very smaller particle size. So we expected that it's
No, not. I'm saying not graphene.
yes.
Why did you take graphene oxide?
Well, sir, graphene oxide is easily available. That is at lower cost available than in graphene.
Question is, why didn't you take reduced graphene oxide or graphene as such? Why did you take graphene oxide?
Properties you can just tell.
At higher temperature, this graphene oxide will reduce to graphene.